a marker in the chat. All right. We are back with the next chapter in the Game Programming Patterns book. We're going to be going through the Data Locality, reading through the chapter, and converting all the exercises into JavaScript. And if at the end we sort of feel that this is a good chapter that would, be good to go through the exercises in Rust, then like the next day, so tomorrow for me, would be to go through that and do the exercises in Rust. But we'll sort of determine that later. Until then, let's go ahead and get started with this. Data locality, intent. Accelerate memory access by arranging data to take advantage of CPU caching. Motivation. We've been lied to. They keep showing us charts with CPU speed goes up and up every year as if Moore's law isn't just a historical observation, but some kind of divine right. Without lifting a finger, we software folks watch our programs magically accelerate just by virtue of new hardware. Chips have been getting faster, though even that's plateauing now, and by this time it actually has fully plateaued. But the hardware heads failed to mention something. Sure, we can process data faster than ever, but we can't get that data faster. So yeah, there's this gap. Memory, it used to be that memory was the fastest thing that we had in our systems, and that we moving that over, like the processor or like the cables or something else, was like the slowest speed. But we certainly need some kind of improvement in memory along Moore's law. Processor and RAM speed relative to their respective speeds in 1980. As you can see, oh okay, then never mind. I was completely wrong. Memory has never been close to the speed of processor. As you can see, CPUs have grown in leaps and bounds, but RAM access is lagging far behind. Data for this is from Computer Architecture, a quantitative approach by John L. Hennessy, David A. Patterson, and Andrea C. Arpacci. Do so, by the way, of Tony Albert's Pitfalls of Object-Oriented Programming. For your super fast CPU to blow through a ream of calculations, it actually has to get the data out of main memory and into registers. As you can see, RAM hasn't been keeping up with increased CPU speeds, not even close. With today's hardware, it can take hundreds of cycles to fetch a byte of data from RAM. If most instructions need data, and it takes hundreds of cycles to get it, how is it that our CPUs aren't sitting idle 99% of the time waiting for data? Actually, they are stuck waiting on memory, an astonishingly large fraction of the time these days, but it's not as bad as it could be. To explain how, let's take a trip to the land of overly long analogies. It's called random access memory because, unlike disk drives, you can theoretically access any piece of it as quick as any other. You don't have to worry about reading things consecutively like you do a disk, or at least you didn't. As we'll see, RAM isn't so random access anymore. A data warehouse. Imagine you're an accountant in a tiny little office. Your job is to request a box of papers and then do some accountancy stuff with them. Add up a bunch of numbers or something. You must do this for specific labeled boxes according to some arcane logic that only makes sense to other accountants. I probably shouldn't have used a job I know absolutely nothing about in this analogy. Thanks to a mixture of hard work, natural aptitude, and stimulants, you can finish an entire box in, say, a minute. There's a little problem, though. All of those boxes are stored in a warehouse in a separate building. To get a box, you have to ask the warehouse guy to bring it to you. He goes and gets a forklift and drives around the aisles until he finds the box you want. It takes him, seriously, an entire day to do this. Unlike you, he's not getting an Employee of the Month anytime soon. This means that no matter how fast you are, you only get one box a day. The rest of the time, you just sit there and question the life decisions that led to this soul-sucking job. One day, a group of industrial designers show up. Their job is to improve the efficiency of operations, things like making assembly lines go faster. After watching you work for a few days, they notice a few things. Pretty often, when you're done with one box, the next box you request is right next to it, on the same shelf in the warehouse. Using a forklift to carry a single box of papers is pretty dumb. There's actually a little bit of spare room in the corner of your office. The technical term for using something near the thing you just used is locality of reference. They come up with a clever fix. Whenever you request a box from Warehouse Guy, he'll grab an entire pallet of them. He gets the box you want, and then some more boxes that are next to it. He doesn't know if you want those, and given his work ethic, clearly doesn't care. He simply takes as many as he can fit on the pallet. He loads the whole pallet and brings it to you. Disregarding concerns for workplace safety, he drives the forklift right in and drops the pallet in the corner of your office. When you need a new box, now, the first thing you do is see if it's already on the pallet in your office. If it is, great. It only takes you a second to grab it and get back to crunching numbers. If a pallet holds 50 boxes and you got lucky and all the boxes you need happen to be on it, you can churn through 50 times more work than you could before. But if you need a box that's not on the pallet, you're back to square one. Since you can only fit one pallet in your office, the warehouse friend will have to take that one back and then bring you an entirely new one. A pallet for your CPU. Strangely enough, this is similar to how CPUs in modern computers work. In case it isn't obvious, you play the role of the CPU. Your desk is the CPU's registers, and the box of papers is the data you could fit in them. The warehouse is your machine's RAM, and that annoying warehouse guy is the bus that pulls data from your main memory into registers. If I were writing this chapter 30 years ago, the analogy would stop there. But as chips got faster, and RAM, well, didn't, hardware engineers started looking for solutions. What they came up with was CPU caching. Modern computers have a little chunk of memory right inside the chip. The CPU can pull data from this much faster than it can from main memory. It's small because it has to fit in the chip, and because the faster type of memory it uses, static RAM or SRAM, is way more expensive. Modern hardware has multiple levels of caching, which is what they mean when you hear L1, L2, L3, etc. Each level is larger but slower than a previous. For this chapter, we won't worry about the fact that memory is actually a hierarchy, but it's important to know. This little chunk of memory is called a cache. In particular, the chunk on the chip is your L1 cache. In my belabored analogy, its part was played by the pallet of boxes. Whenever your chip needs a byte of data from the RAM, it automatically grabs a whole chunk of contiguous memory, usually around 64 to 128 bytes, and puts it in the cache. This dollop of memory is called a cache line. So, cache line. So we have the byte we registered looks like it's right in the center, right in the middle. And then it's going to get a little bit to the left, a little bit to the right. Let's be, good morning. You wonder if any good testing has been done on how data locality affects performance with the various JavaScript engines. Ooh, that's actually a really good question. Yeah, that would be really interesting to see if they're pulling out memory. But then again, I wonder if the way we write code is really important with that, right? Because if we're using objects, it's just storing those objects all across memory. I wonder if arrays in JavaScript are contiguous. I thought that they were, and then I thought that they weren't, and then I thought that they were again, and so now I'm just like, I'm not sure anymore. I'm not sure what's true. If the next byte of data you need happens to be in that chunk, the CPU reads it straight from the cache, which is much faster than hitting RAM. Successfully finding a piece of data in the cache is called a cache hit. If you can't find it in there and has to go to main memory, that's a cache miss. I glossed over at least one detail in the analogy. In your office, there is only room for one pallet or one cache line. A real cache contains a number of cache lines. The details about how those work is out of scope here, but search for cache associativity to feed your brain. Oh, interesting. So you could pull a lot more. When a cache miss occurs, the CPU stalls. It can't process the next instruction because it needs data. It sits there, bored out of its mind for a few hundred cycles until the fetch completes. Our mission is to avoid that. Imagine you're trying to optimize some performance-critical piece of game code, and it looks like this. All right, so we have, we're looping through a number of things, sleep for 500 cycles, then do one of the things. Fairly inefficient there. What's the first change you're going to make to the code? Right, take out that pointless, expensive function call, sleep for 500 cycles. That call is equivalent to the performance cost of a cache miss. Every time you bounce to main memory, it's like you put a delay in your code. Wait, data is performance? When I started working on this chapter, I spent some time putting together little game-like programs that would trigger best case and worst case cache usage. I wanted benchmarks that would thrash the cache so I could see firsthand how much bloodshed it causes. When I got some stuff working, I was surprised. I knew it was a big deal, but there's nothing quite like seeing it with your own eyes. I wrote 2 programs that did the exact same computation. The only difference was how many cache misses they caused. The slow one was 50 times slower than the other. There are a lot of caveats here. In particular, different computers have different cache setups, so my machine may be different from yours, and dedicated game consoles are very different from PCs, which are quite different from mobile devices. Your mileage will vary. I wonder if like dedicated consoles, like the PS5, the Xbox One X or whatever the new one is called, the Switch, I wonder if those have larger caches, and so it's easier to sort of like plan out this cache hitting. This was a real eye-opener to me. I'm used to thinking of performance being an aspect of code, not data. A byte isn't slow or fast, it's just some static thing sitting there. But because of caching, the way you organize data directly impacts performance. The challenge now is to wrap that up into something that fits into a chapter here. Optimization for cache usage is a huge topic. I haven't even touched on instruction caching. Remember, code is in memory too, and it has to be loaded onto the CPU before it can be executed. Someone more versed on this subject could write an entire book on it. In fact, someone did write a book on it. Data-Oriented Design by Richard Fabian. Since you're already reading this book now, though, I have a few basic techniques that will get you started along the path of thinking about how data structures impact your performance. It all boils down to something pretty simple. Whenever the chip reads some memory, it gets a whole cache line. The more you can use stuff in that cache line, the faster you go. So the goal then is to organize your data structures so that the things you're processing are next to each other in memory. There's a key assumption here, though: one thread. If you're modifying nearby data on multiple threads, it's faster to have it on different cache lines. If 2 threads try to tweak data on the same cache line, both cores have to do some costly synchronization of their caches. In other words, if your code is crunching on thing, then another, then also, you want them laid out in memory like this. So thing, another, also, but like not, interesting. Good morning, Bare Knuckle Waffle. Thank you for highlighting that, all the Rusty messages. Oh, I forgot the name of the rest. Oh man, what's the little guy's name? Ferris. I highlighted Ferris. Thank you. Note that these aren't pointers to thing, another, and also. This is the actual data for them, in place, lined up one after the other. As soon as the CPU reads in thing, it'll start to get another, and also alt 2, depending on how big they are and how big a cache line is. When you start working on next to them, they'll already be cached. Your chip is happy, and you're happy. The pattern. Modern CPUs have caches to speed up memory access. These can access memory adjacent to recently accessed memory much quicker. Take advantage of that to improve performance by increasing data locality, keeping data in contiguous memory in the order that you process it. When to use it. Like most optimizations, the first guideline for using the data locality pattern is when you have a performance problem. Don't waste time applying this to some infrequently executed corner of your database. Optimizing code that doesn't need it just makes your life harder, since the result is almost always more complex and less flexible. With this pattern specifically, you'll also want to be sure your performance problems are caused by cache misses. If your code is slow for other reasons, this won't help. The cheap way to profile is to manually add a bit of instructions that check how much time has elapsed between 2 points in the code, hopefully using a precise timer. To catch poor cache usage, you'll want something a little bit more sophisticated. You really want to see how many cache misses that are occurring and where. Fortunately, there are profilers out there that report this. It's worth spending the time to get one of these working and make sure you understand the surprisingly complex numbers it throws at you before you do major surgery in your data structures. Unfortunately, most of those tools aren't cheap. If you're on a console dev team, you probably already have licenses for them. If not, an excellent free option is Cache Grind. It runs your program on top of a simulated CPU and cache hierarchy, and then reports all of the cache interactions. That being said, cache misses will affect the performance of your game. While you shouldn't spend a ton of time preemptively optimizing for cache usage, do think about how cache-friendly your data structures are throughout the design process. Keep in mind, one of the hallmarks of software architecture is abstraction. A large chunk of this book is about patterns to decouple pieces of code from each other so that they can be changed more easily. In object-oriented languages, this almost always means interfaces. In C++, using interfaces implies accessing objects through pointers or references. But going through a pointer means hopping across memory, which leads to the cache misses this pattern works to avoid. The other half of interfaces is virtual method calls. Those require the CPU to look up an object's vtable and then find the pointer to the actual method to call there. So again, you're chasing pointers, which can cause cache misses. In order to please this pattern, you will have to sacrifice some of your precious abstractions. The more you design your program around data locality, the more you will have to give up inheritance, interfaces, and the benefits those tools can provide. There's no silver bullet here, only challenging trade-offs, and that's what makes it fun. Of course, in JavaScript, we don't really have interfaces. We have to sort of like make it up by just using, just inheriting from another full class. So we don't necessarily give up anything in JavaScript for this. Sample code. If you really go down the rat hole of optimizing for data locality, you'll discover countless ways to slice and dice your data structures into pieces your CPU can most easily digest. To get started, I'll show you an example for each of the few of the most common ways to organize your data. We'll cover them in the context of some specific part of a game engine, but as with other patterns, keep in mind that the general technique can be applied anywhere it fits. Contiguous arrays. Let's start with a game loop that processes a bunch of game entities. Those entities are decomposed into different domains, AI, physics, and rendering, using the component pattern. Here's the game entity class. All right, so time for us to start doing some coding. I'm going to create a new file here, and we're going to call this data locality.js. And so we're going to start with a class game entity. So class game entity. And we're going to have a constructor for this. And inside the constructor, we're going to take in an AI We're going to take in the physics component and the render component. And it looks like we're just going to store them internally. So this dot AI equals AI. This dot physics equals physics. This dot render equals render. And then we're going to have methods to return these. So we're going to have AI, and this returns AI. We're going to have physics, which return this dot physics. And then the same with render. Each component has a relatively small amount of state, perhaps little more than a few vectors or a matrix, and then a method to update it. The details aren't important here, but imagine something roughly along the lines of... Okay, so we have now we're going to create each of these. So like we have the AI, the physics, and the render. So we're going to have class, AI component. We're going to have an update method. So this obviously like updates like the AI. Like I don't really know if there's much I need to like do comment wise. It should be pretty obvious what we're doing. Now also goals, mood, like to figure like anything to support update also goes in here. Physics component class physics component, and this has the update method, and class render component, which also has update. The game maintains a big array of pointers to all the entities in the world. Each spin of the game loop, we need to run the following. Update the AI components for all of the entities, update the physics components for them, render them using their render components. Lots of game engines implement that, like so. Okay, so then we're having like in the actual run. So in the update loop. So while not game over, so just to make sure that this runs properly, let's create. Let's game over equals false. So while not game over, we are going to have to loop over the number of these entities and then process them. So we're going to have this entities array. So probably in setup, we're going to need like const entities equals an array. And that's going to be these game entities. So we could have like new game entity, which then itself takes in a new AI component, new let's see, physics component, and a new render component. And this could be repeated several times. So there we have three entities, and whatever these are, and it almost doesn't matter what they are. We can define them like, okay, this is the player, this is an AI, and this is a spike in the world. But here we have to loop through all of these. So a forever game loop, and then for let index equals 0, index is less than, what is these, entities? Entities.length, entities plus equals to 1, and then we're just going to run update for each of these. Okay, so process the EI first, and then process all the physics, then process all the renders. So then we're going to do entities of position index dot AI dot update, like that. And then we're copy this twice more, and so now it's going to be AI and then physics and then render. Before you ever heard of a CPU cache, this looked totally innocuous, but by now you've got an inkling that something isn't right here. This code isn't just thrashing the cache, it's taking it around back and beating it to a pulp. Watch what it's doing. The array of game entities is storing pointers to them. So for each element in the array, we have to traverse that pointer. That's a cache miss. Then the game entity has a pointer to the component. Right here. That's another cache miss. Then we update the component. Now we go back to step 1 for every component of every entity in the game. The scary part is that we have no idea how these objects are laid out in memory. We're completely at the mercy of the memory manager. As entities get allocated and freed over time, the heap is likely to become increasingly randomly organized. So we can see here, like, okay, well, here's all these different entities, and then they're pointing to like these areas and memory. It's not trying to show them in like a hierarchical, not graph, but like a list, sort of like what a lot of memory would show us. It's more of, hey, they're just all over the place. And when we grab something, we grab a chunk of it, but it's probably not the right chunk. Every frame, the game loop has to follow all of those arrows to get the data it cares about. If our goal was to take a whirlwind tour around the game's address space, like some 256 megabytes of RAM and 4 nights, cheap vacation package, this would be a fantastic deal. But our goal is to run the game quickly, and traipsing all over main memory is not the way to do that. Remember that sleep for 500 cycles function? Well, this code is effectively calling that all the time. The term for wasting a bunch of time traversing pointers is pointer chasing, which it turns out is nowhere near as fun as it sounds. Let's do something better. Our first observation is that the only reason we follow a pointer is to get to the game entity is so we can immediately follow another pointer to get to a component. Game entity itself has no interesting state and no useful methods. The components are what the game loop cares about. Instead of a giant constellation of game entities and components scattered across the inky darkness of address space, we're going to get back down to earth. We'll have a big array for each type of component, a flat array of AI components, another for physics, and another for rendering, like this. Okay, so AI component equals AI components, new AI component, max entities. So notice that these are now just an array of all the AI components. And we don't have a game entity at all. We just have AI components instead. My least favorite part about using components is how long the word component is. Let me stress that these are arrays of components and not pointers to components. The data is all there, one byte after the other. The game loop can then walk these directly. Okay, so where we have for num entities, loop through all the number entities, AI components that update, physics components. Oh, right. Okay, so we're no longer doing the same thing here. So to change this around, in our setup, instead of this like game entity like this, I'll comment this out. Now what we're going to do is we're going to have, wait, that's in. Okay, so now we're going to have const, and this is going to be AI components without the capitalization, equals, and it's just going to be an array. And so if, let's say we had 3 of these, we're going to have new AI component like this, new AI component, new AI component. And this would be for, the 3 AI components that we have for the 3 entities. And then we repeat these. So you are going to be the physics components, and you're going to be the render components. So new physics component and render component. Component. Oh, that was. Did I really? I did. I misspelled render component. Let's fix that really quickly. Render component. There we go. Interesting that it decided that this one doesn't need to be lined up, but these ones do. I guess like the name of AI component is just not enough to be underneath whatever arbitrary line width that I have for. I think it's prettier that I've got going on. Okay, so now in our game loop, instead of this, we're still going to do the three for loops. So maybe it's actually not quite bad like that. We're going to go like this. Now we probably do want some kind of count here to count that they're all the same. So every time that we register something, it's probably best for us to kind of like do some kind of assert. So if the AI components dot length does not equal the physics component dot length, and AI components dot length does not equal the render components dot length, that should be good enough. If that's like, if this is true, then we want to throw new error. We must have the same number of components. And I know that in some ECS systems, they can handle different numbers of components. But obviously for this one that we have, that's not exactly the case. So if we do this trek, if we do this, we can now know that we can set up entities. Also, you need to be index. You're not gonna index +1, index +1, index. Now in here, I want you to now be the, let's just do AI components. And it doesn't really matter which one we choose because we're just getting the index number of it. And then that will allow me to come in here and say, okay, we want the AI components of position index dot update. And it's very similar. If I copy you, paste, you are now going to be the physics components, and then finally, the render components. All right, that should be updated for this. Those arrays of components are references though, aren't they? Is it even possible to do arrays of objects in JavaScript? Yeah, that's the thing is structs, and it does make me curious, like in C++, how this works too. Are objects like contiguous in memory? And then the other thing, are objects contiguous in memory in JavaScript, as long as we don't have like things that are passed by reference? The problem here is that update is a method. Methods are passed by reference by default. So this doesn't work at all, which is unfortunate. One hint that we're doing better here is how few arrow operators there are in a new code. If you want to improve data locality, look for indirection operators that you can get rid of. Why wouldn't it work? So the problem we have here is in JavaScript. So we're talking about JavaScript here. Methods are passed by reference. There's nothing you can do about this. They're passed by reference. Objects are passed by reference. Only like primitive data is passed by value. And what that ends up meaning is this entire thing that we're doing here to try to make sure that it's contiguous in memory, that like, okay, we have like everything that we need for AI. The problem that we're having is, okay, the first AI components update, this isn't next to each other. This update isn't here. It might be way over here. It might be over here. It might be everywhere else. And that's just a JavaScript thing. Now, if we, this feels, I still don't know if this feels like we're packing up the data properly. If we want to pack up the data in such a way, we probably need to break it down even more and start doing something like AI, like like I don't know what data we need for the AI. I haven't really done much AI type stuff. It might be more of like the X positions. So like locations. So we can say something like positions. Positions of data. Let's do const positions equals, and then this will have to be an array, and now I have to stay in primitive values. I can't even do like arrays of arrays because arrays are passed by reference. So I'd have to do something like the X is like 150 and then 25, and this would be the XY pair. And then the next entity would be, coming up. So like 333. Like, then this would be the next XY pair. This really sucks when it comes to sort of figuring out and looking at this as a human and seeing, okay, here's the location of the first entity. And we know this first entity is, let's say, Pac-Man. And the second entity is the ghost. And the third entity is like the next ghost. That really sucks for like actually being able to do, to like see this. Probably having something that almost like a compiler for us, where we can write it in one code and have it like then create the data that we need. And then we store that. That would probably be best for us as developers. Okay. So like code to help us write the code. All right. We've ditched all that pointer chasing. Instead of skipping around in memory, we're doing a straight crawl through the 3 contiguous arrays. This pumps a solid stream of bytes right into the hungry maw of the CPU. In my testing, this change made the update loop 50 times faster than the previous version. Interestingly, we haven't lost much encapsulation here. Sure, the game loop is updating the components directly instead of going through the game entities, but it was doing that before to ensure that they were processed in the right order. Even so, each component itself is still nicely encapsulated. It owns its own data and methods. We simply change the way it's used. This doesn't mean we need to get rid of game entity either. We can leave it as it is, with pointers to its components. They'll just point into those arrays. This is still useful for other parts of the game. We want to pass around the conceptual game entity and everything that goes with it. The important part is that the performance-critical game loop sidesteps that and goes straight to the data. Packed data. Let's see. According to Bo. Also, I forgot to say hello. Good morning. If you need more tight memory control, I guess JS isn't the best place to do it. Maybe Wasm? Wasm is still going to be running in the JavaScript, engine. So I think like even that is going to run into the same problem. Maybe Wasm might help you write code that looks better, and then it compiles to like a better system. But it's still going to have run into the same problems. I don't know. I think we just have to think about it in a very particular, like be very cognizant about it, and then go from there. Okay, so say we're doing a particle system. Following the advice of the previous section, we've got all of our particles in a nice big contiguous array. Let's wrap it in a little manager class too. The particle system class is an example of an object pool custom built for a single type of object. All right, so we have our class particles. Let's come back up here. What's all this from? This is all like us creating these. Let's do it up here. Class particle. So we're gonna have this particle system. Have a constructor, and the constructor is gonna take in the number of particles, or rather, it's going to store that internally. So this dot num particles, and we're going to instantiate that to 0, and then we're going to have an update method, which well, this looks like void update that's not doing anything. And then we're going to have max particles. So we're going to have this dot max particles equals, what is that, 100,000? Nice. And then we're going to create our array of particles. So this dot particles. Now this one we're like creating the array to begin with. So new array, and then the array length, which is going to be this dot max particles, like that. Let's see. Rizix, good morning. Looks like an array buffer would help with contiguous data, but you have to be explicit with the buffer offsets. It's part of typed array specification. And then Usby, I think you just hope you're giving the JS engine enough clues to do something sensible. Heading down the route of manually packing and unpacking primitive binary buffers seems counterproductive in the long run. Yeah, it might be, and it might just be that in JavaScript we just say, you know what? We're not going to be able to use the CPU that fast. That being said, I know that C++ for Chrome is doing some amazing things with your code before it runs it, sort of like that compilation step as it turns it into machine code. So there's some, I wonder if it's possible that you can optimize your code for the compiler to do some really interesting things with the data that way. With type of and stuff, you should probably easily get a good set of utility functions. Absolutely, yeah. A rudimentary update method for the system just looks like this. Okay, so now we're going to update. We're going to update here. We're going to loop through all of our particles. So for let index equals 0, index is less than this dot num particles, and then index plus equals to 1. And then we're going to do this dot particles of index dot update. But it turns out that we don't actually need to process all of the particles all the time. The particle system has a fixed size pool of objects, but they aren't usually all actively twinkling across the screen. The easy answer is something like this. Okay, so we're going to loop through all the particles, check to see if the particle is active, and then update it. So this first. So if this dot particles dot of position index dot is active, then we update the particle. We give particle a flag to track whether or not it's in use or not. In the update loop, we check that for each particle. That loads the flag into the cache along with all of that particle's other data. If the particle isn't active, then we skip over to the next one. The rest of the particle's data that we loaded into the cache is a waste. The fewer active particles there are, the more we're skipping across memory. The more we do that, the more data caches we miss. The more cache misses there are between actually doing anything useful. Man, I'm not reading this sentence right. Let's try it again. The more we do that, the more cache misses there are between actually doing useful work updating active particles. If the array is large and has lots of inactive particles in it, we're back to thrashing the cache again. Having objects in a contiguous array doesn't solve much if the objects we're actually processing aren't contiguous in it. If it's littered with inactive objects, we have to dance around. We're right back to the original problem. Savvy, low-level coders can see another problem here. Doing an if check for every particle can cause a branch misprediction and a pipeline stall. In modern CPUs, a single instruction actually takes several clock cycles. To keep the CPU busy, instructions are pipelined so that the subsequent instruction starts processing before the first one finishes. To do that, the CPU has to guess which instructions will be executing next. In straight-line code, that's easy, but with control flow, it's harder. While it's executing the instructions for that if, does it guess that the particle is active and start executing the code for the update call? Or does it guess that it isn't? To answer that, the chip does branch prediction. It sees which branches your code previously took and guesses that it will do that again. But when the loop is constantly toggling between particles that are and are not active, that prediction fails. When it does, the CPU has to ditch the instructions it had started speculatively processing, a pipeline fresh, and start over. The performance impact of this varies widely by machine, but this is why you sometimes see developers avoid flow control in hot code. Given the title of this section, you can probably guess the answer. Instead of checking the active flag, we'll sort by it. We'll keep all of the active particles in the front of the list. If we know all of those particles are active, we don't have to check the flag at all. We can also easily keep track of how many active particles there are. With this, our update loop turns into this thing of beauty. Okay, so then we're back to not having this if check. And we're just, but now it's num active. So now we need this dot num active, and we're going to start with 0 because we have nothing active. So this dot num active. Now we aren't skipping over any data. Every byte that gets sucked into the cache is a piece of active particle that we actually need to process. Of course, I'm not saying you should quicksort the entire collection of particles every frame. That would more than eliminate the gains here. what we want to do is keep the array sorted. Assuming the array is already sorted, and it is at first when all particles are inactive, the only time it can become unsorted is when a particle has been activated or deactivated. We can handle those two cases pretty easily. When a particle gets activated, we move it to the end of the particles array by swapping it with the first inactive one. Okay, so now we're gonna have the particle system activate particle. So activate particle, and we're going to take in the index of the particle to activate. So let's see, they're asserting that index is not greater than num active. Okay, so shouldn't already be active. Now this is the equivalent of doing an if and then a throw here. So if this dot, I guess if index is, we need this to be greater than or equal to num active. Shouldn't already be active. So if it's greater than num active, we're activating a particle. Okay, never mind. I had it like backwards in my mind that we were deactivating a particle, even though I wrote out activate particle. Fun. Okay, so we want to make sure it's on the right-hand side of the array, that it's like way over there. So if we have here's where the active line ends, here's where all of our deactivated particles are. So we need to grab one of them. So we're going to grab, let's see, index. We want, if index is less than this dot num active, you want to throw new error, and the message is attempting to activate active particle. Save that. Then we can actually do the work here. Okay, so swap it with the first inactive particle right after the active ones. So it's a Towers of Hanoi type problem. If any of you have done like any kind of like quicksort or anything else, this is a pretty simple pattern that we do all the time. So we have a const, our temp particle equals this dot particles of position num active. So that's gonna be the first inactive one. And then we're gonna do particles of position num active. And then we're gonna swap this with the index one. So this dot particles of position index. And then we're gonna put the num active at the index, right? Yeah. This dot index, so particles index equals temp. And then finally, the most important part here, this dot num active, we have to increment it, otherwise bad things happen. To deactivate a particle, we do exactly the opposite. Okay, so let's deactivate a particle next. So deactivate particle here. We're also going to take in an index. And so we're going to have the same assertion essentially. So if our index is greater than this dot, it's going to have to be greater than or equal to this dot num active. Might as well do this like this, throw new error. Attempting to deactivate a deactivated particle. And then we're going to have our entire like swap and everything else. Now with this one, we're decrementing num active first. So this dot num active minus equals to 1. And then we do our entire swap system. So we do our temp first. So const temp equals this dot particles of position num active. So inside the brackets, please. And then we do our particle. So this dot particles of position, this dot num active, and then we set that equal to this dot particles of index, and this dot particles of position index equals temp. Lots of programmers, myself included, has developed allergies to moving things around in memory. Schlepping a bunch of bytes around feels heavyweight compared to assigning a pointer. But when you add in the cost of traversing that pointer, it turns out that our intuition is sometimes wrong. In some cases, it's cheaper to push things around in memory if it helps you keep the cache full. This is your friendly reminder to profile when making these kinds of decisions. There's a neat consequence of keeping the particles sorted by their active state. We don't need to store an active flag in each particle at all. It can be inferred by its position in the array and the num active counter. This makes our particle object smaller, which means we can pack more in our cache lines, and that makes them even faster. It's not all rosy though. As you can see from the API, we've lost a bit of object orientation here. The particle class no longer controls its own active state. You can't call some activate method on it since it doesn't know its index. Instead, any code that wants to activate particles needs access to the particle system. In this case, I'm okay with particle system and particle being tightly tied like this. I think of them as a single concept, spread across two physical classes. It just means accepting the data and that particles are only meaningful in the context of some particle system. It also in this case, it's likely to be the particle system that will be spawning and killing particles anyway. Hot-cold splitting. Okay, this is the last example of a simple technique for making your cache happier. Say we've got an AI component for some game entity. It has some state in it. The animation it's currently playing, a goal position it's heading towards, energy level, etc. Stuff it checks and tweaks every single frame. Something like, okay, so we have our AI component. So we're back here. So we have our class, AI component. We have that up here. Here's our AI component. We have our update method. And then we also have animation, energy, and goal position. So I think this will be under constructor. So we're going to do this dot animation. We don't necessarily know what these are. Maybe they're passed in. So when we create it, so let's do that. Animation gets passed in. Animation. This dot energy. Add these in here first. Energy and then goal position. Okay, so energy equals energy. This dot goal position equals goal position. But it also has some state for rare eventualities. It stores some data describing what loot it drops when it has an unfortunate encounter with the noisy end of a shotgun. That drop data is only used once in the entity's lifetime, right at its bitter end. So that means we're also going to store the loot drop. So the drop, maybe we'll call this loot. This is going to be loot drop. Now, interesting enough, we have min drops, max drops, chance of drop. Interesting. So we have like what it's going to drop. So it's going to be the loot, min drops, max drops, min drops, max drops, chance drop. So like it is making this a little bit more bulky of like constructor for this, but we're not optimizing for sort of like developer niceties. We're optimizing for like the cache niceties. So this dot loot equals loot. This dot min drops equals min drops. This dot max drops equals max drops. This dot chance of drop equals chance of drop. Now that being said, this isn't as bad as it used to be. Like there's that entire idea of clean code where you should now have like one single thing being passed into an object or a function at any one time. This makes it so that there obviously there's a lot more, and it's a lot more complicated, but the tooling that our editors provide is actually really nice these days. So in that case, it helps out as well. Okay, so we're storing all that. Assuming we followed the earlier patterns, when we update these AI components, we walk through a nice packed contiguous array of data. But that data includes all of the loot drop information. That makes each component bigger, which reduces the number of components we can fit in a cache line. We get more cache misses because the total memory we walk over is larger. The loot data gets pulled into the data cache for every component in every frame, even though we aren't touching it. The solution for this is called hot-cold splitting. The idea is to break our data structure into two separate pieces. The first holds the hot data, the state we need to touch every frame. The other piece is the cold data, everything else that gets used less frequently. The hot piece is the main AI component. It's the one we need to use the most, so we don't want to chase a pointer to find it. The cold component can be off to the side, but we still need to get to it. So we give the hot component a pointer to it, like so. All right, so we have AI component. And this takes, so we have our public methods, our animation. So here's our animation. We have our energy. We have our goal position, where it's going to. And then we have loot. So what that looks like here is this class loot drop that has a constructor. And the constructor is going to hold all these things now. So we're still going to take in the loot, min drops, max drops when we create the AI component, because we're only doing that once. But all of this now gets stored in here. So let's take a look at this. Chance drops, min drops, and then the loot itself. So copy this, and in the constructor, here you go. Now, we don't need to store any of that in here. And also in our constructor, over here in loot drop, we're gonna have to do you all get run down here. So our constructor takes in the loot, min drops, max drops, and chance drops, and then stores them internally. Then in here, we're not going to store these. Instead of loot here, we're going to do a new loot drop, and then pass in the loot, the min drops, the max drops, and the chance of drop. Now when we're walking the AI components every frame, the only data that gets loaded into the cache is stuff we're actually processing, with the exception of that one little pointer to the cold data. We could conceivably ditch the pointer too by having parallel arrays for the hot and cold components. Then we can add the cold AI data for a component, since both pieces will be at the same index in their respective arrays. You can see how this starts to get fuzzy though. In my examples here, it's pretty obvious which data should be hot and cold. But in a real game, it's rarely so clear cut. What if you have fields that are used when an entity is in a certain mode, but not in others? What if entities use a certain chunk of data only when they're in certain parts of the level? Doing this kind of optimization is somewhere between a black art and a rat hole. It's easy to get sucked in and spend endless time pushing your data around to see what speed difference it makes. It will take practice to get a handle on where to spend your effort. Assign decisions. This pattern is really about a mindset. It's getting you to think about your data's arrangement in memory as a key part of your game's performance story. The actual concrete design space is wide open. You can let data locality affect your whole architecture, or maybe it's just a localized pattern you apply to a few core data structures. The biggest questions you'll need to answer are when and where you apply this pattern, but here are a couple of others that may come up. Noah Lopez's famous article that got a lot more people thinking about designing games around cache usage calls this data-oriented design. How do you handle polymorphism? Up to this point, we've avoided subclassing in virtual methods. We have assumed we have nice packed arrays of homogeneous objects. That way, we know they're all exact same size. But polymorphism and dynamic dispatch are useful tools too. How do we reconcile this? Well, don't. The simplest answer is to avoid subclassing, or at least avoid it in places where you're optimizing for cache usage. Software engineer culture is drifting away from heavy use of inheritance anyway. One way to keep much of the flexibility of polymorphism without using subclasses is through the type object pattern. It's safe and easy. You know exactly what class you're dealing with, and all objects are obviously the same size. It's faster. Dynamic dispatch means looking up the method in the vtable and then traversing that pointer to get the actual code. While the cost of this varies widely across different hardware, there is some cost to dynamic dispatch. As usual, the only absolute is that there are no absolutes. In most cases, a C++ compiler will require an indirection for a virtual method call, but in some cases, the compiler may be able to do de-virtualization and statically call the right method if it knows what concrete type the receiver is. De-virtualization is more common in just-in-time compilers for languages like Java and JavaScript. It's inflexible. Of course, the reason we use dynamic dispatch is because it gives us a powerful way to vary behavior between objects. If you want different entities in your game to have their own rendering styles or their own special moves and attacks, virtual methods are a proven way to model that. Having to instead fluff all that code into a single non-virtual method that does something like a big switch gets messy quickly. Use separate arrays for each type. We use polymorphism so that we can invoke behavior on an object whose type we don't know. In other words, we have a mixed bag of stuff. We want each object in there to do its own thing when we tell it to go. But that raises the questions of why we mix the bag to begin with. Instead, why not maintain separate homogeneous collections for each type? It keeps objects tightly packed. Since each array only contains objects of one class, there's no padding or other weirdness. You can statically dispatch. Once you've got objects partitioned by type, you don't need polymorphism at all anymore. You can use regular non-virtual method calls. You have to keep track of a bunch of collections. If you have a lot of different object types, the overhead and complexity of maintaining separate arrays for each can be a chore. You have to be aware of every type. Since you have to maintain separate collections for each type, you can't be decoupled from the set of classes. Part of the magic of polymorphism is that it's open-ended. Code that works with an interface can be completely decoupled from the potentially large set of types that implement that interface. Use a collection of pointers. If you weren't worried about caching, this is the natural solution. You just have an array of pointers, to some base class or interface type. You get all the polymorphism you could want, and objects can be whatever size you want. It's flexible. That code that consumes the collection can work with objects of any type, as long as it supports the interface you care about. It's completely open-ended. it's less cache friendly. Of course, the whole reason we're discussing other options here is because this means cache unfriendly pointer indirection. But remember, if this code isn't performance critical, that's probably okay. How are game entities defined? If you use this pattern in tandem with the component pattern, you'll have nice contiguous arrays for all of the components that make up your game entities. The game loop will be iterating over those directly, so the object for the game entity itself is less important, but it's still useful in other parts of the codebase where you want to work with a single conceptual entity. The question then is, how should it be represented? How does it keep track of its components? If game entities are classes with pointers to their components, this is what our first example looks like. It's sort of the vanilla OOP solution. You've got a class for a game entity and has pointers to the components it owns. Since they're just pointers, it's agnostic about where and how those components are organized in memory. You can store components in contiguous arrays. Since the game entity doesn't care where its components are, you can organize them in a nice, packed array to optimize iterating over them. Given an entity, you can easily get to its components. They're just a pointer indirection away. Moving components in memory is hard. When components get enabled or disabled, you may want to move them around in the array to keep the active ones up front and contiguous. If you move a component while the entity has a raw pointer to it, though, that pointer gets broken if you aren't careful. You have to make sure to update the entity's pointer at the same time. If game entities are classes with IDs for their components, the challenge with raw pointers to components is that it makes it harder to move them around in memory. You can address that by using something more abstract, an ID or index that can be used to look up a component. The actual semantics of the ID and lookup process are up to you. It could be as simple as storing a unique ID in each component walking the array, or more complex, like a hash table that maps IDs to the current index in the component's array. That's what I was sort of like going through in this temporary idea down here that I deleted, which is we have like const, like locations, equals, and then this would be an array of like the XY. So like, 120, 15 would be like X and Y for, in JavaScript, for the locations of like each entity. And then we can say, okay, well, it's odd, so every odd index. So we could have, then we want to store all the players, so we can, if we loop through knowing that it has to be even, then like player is really index 0 and 1. Like that's its XY. And then AI would be this next one. So that would be like maybe 325. AI index is starts at position 2. And then we can just loop through it and say, oh, every 2. So play, every index, loop through by 2, and then update the locations. So we can have velocities, accelerations, following this exact same pattern here. Where did I end up with this? I forgot where I stopped. It's more complex. Your ID system doesn't have to be rocket science, but it's still more work than a basic pointer. You have to implement and debug it, and there will be memory overhead for bookkeeping. It's slower. It's hard to beat traversing a raw pointer. There may be some searching or hashing involved to get from an entity to one of its components. You'll need access to the component manager. The basic idea is that you have some abstract ID that identifies a component. You could use it to get a reference to the actual component object, but to do that, you need to hand that ID to something that can actually find the component. That will be the class that wraps your raw contiguous array of component objects. With raw pointers, if you have a game entity, you can find its components. With this, you need the game entity and the component registry too. You may be thinking, I'll just make it a singleton. Problem solved. Well, sort of. You might want to check out the chapter on those first. We're at the home stretch. If the game entity is itself just an ID, this is a newer style that some game engines use. Once you've moved all of your entity's behavior and state out of the main class and into components, what's left? It turns out not much. The only thing an entity does is bind a set of components together. It exists just to say this AI component and this physics component and this render component define one living entity in the world. That's important because components interact. The render component needs to know where the entity is, which may be a property of the physics component. The AI component wants to move the entity, so it needs to apply a force to the physics component. Each component needs a way to get the other sibling components of the entity it's a part of. Some smart people realize all you need for that is an ID. Instead of the entity knowing its component, the components know their entity. Each component knows the ID of the entity that owns it. When the AI component needs the physics component for its entity, it simply asks for the physics component with the same entity ID that it holds. Your entity classes disappear entirely, replaced by a glorified wrapper around a number. Entities are tiny. When you want to pass around a reference to a game entity, it's just a single value. Entities are empty. Of course, the downside of moving everything out of entities is that you have to move everything out of entities. You no longer have a place to put non-component specific state or behavior. This style doubles down on the component pattern. You don't have to manage their lifetime. Since entities are just dumb value types, you don't need to be explicitly allocated and freed. An entity implicitly dies when all of its components are destroyed. Looking up a component for an entity may be slow. This is the same problem as the previous answer, but in the opposite direction. To find a component for some entity, you have to map an ID to an object. That process may be costly. This time, though, it is performance critical. Components often interact with their siblings during update, so you will need to find components frequently. One solution is to make the ID of an entity the index of the component in its array. If every entity has the same set of components, then your component arrays are completely parallel. The component in slot 3 of the AI component array will be for the same entity that the physics component in slot 3 of its array is associated with. Keep in mind, though, that this forces you to keep those arrays in parallel. That's hard if you want to start sorting or packing them by different criteria. You may have some entities with disabled physics and others that are invisible. There's no way to sort the physics and render component arrays optimally for both cases if they have to stay in sync with each other. See also, much of this chapter revolves around the component pattern, and this pattern is definitely one of the most common data structures that gets optimized for cache usage. In fact, using the component pattern makes this optimization easier, since entities are updated one domain, AI, physics, etc. at a time. Splitting them out into components lets you slice a bunch of entities into the right pieces to be cache friendly. But that doesn't mean you can only use this pattern with components. Anytime you have performance critical code that touches a lot of data, it's important to think about locality. Tony Albrecht's Pitfalls of Object-Oriented Programming is probably the most widely read introduction to designing your game's data structures for cache friendliness. It made a lot more people, including me, aware of how big a deal this is for the performance. Oh, it's a PDF right here. So that's actually just available if it loads. Around the same time, Noel Lopez wrote a very influential blog post on the same topic. This pattern almost invariably takes advantage of a contiguous array of homogeneous objects. Over time, you'll very likely be adding and removing objects from that array. The object pool pattern is about exactly that. The Artemis game engine is one of the first and better known frameworks that uses simple IDs for game entities. This isn't loading, so my guess is it's not properly loaded there anymore. How about this blog post? Does that work? Yes, it does. Okay, so I'll share this out. So that's this article here for data locality. And we are done with this. So let me go ahead and save that. Let's open up Git Kraken and send this code on up to GitHub. So in our learning game engines here, we'll store this and read through data locality. Let's see, converted examples to JavaScript. Save that. push this on up. So all the code you can find with Bang repo. It would help if I spell that correctly. Bang repo. And if you're watching this as a VOD, I will have the link to the code in the description. And with that, we're done with this chapter. So tomorrow or the next video, I'm planning on going through this chapter again and converting the examples to Rust, because this looks like the perfect example for Rust code. So we can look forward to that tomorrow. I'm gonna put in a marker to end the video for